I suppose that we've come to that day. When you talk about spectral graph theory, there are sort of two big things that people always think about as your sort of entry into spectral graph theory. And one is that the adjacency matrix is really good at counting walks. And we've already talked about that. So that leaves us with the second thing, which is today, which is Kirchhoff's Matrix Tree Theorem. And this says, hey, you can relate eigenvalues to trees. And more particularly, you can do the following. So I'll go ahead and state.
Is it CH in their name?
Yes, okay. Yes. That or it's a new letter I've created. So, yes. No, it's all right. You should check me. All right. And so what's the punchline? So given a graph G with the eigenvalues of the Laplacian, all right, just L sub G, so the Laplacian matrix for the graph G are, well, 0 will always be our first eigenvalue, and then we'll just weakly order them. So that's usually, we'll do something like lambda 1, lambda 2, up to lambda n. That's our assumptions. So pretty safe assumptions. And then the conclusion is, then the number of spanning trees of G is 1 over n times lambda 2 up to lambda n multiplied together. And I know I didn't explicitly state that G is a graph on n vertices. I did implicitly state that. Where is it implicitly stated that G is a graph on n vertices? Yeah, there are n eigenvalues. So this is where that n is coming from. All right. So, all right.
Even if lambda 2 is also 0,
yes. So let's think about it. What does it mean for lambda 2 to be 0? So if lambda 2 equals 0, then that's not connected. And, well, so that says you have something over here, and you have something over here. And the problem is there can't be a spanning tree. So I guess we should stop and say, what is a spanning tree? All right, maybe we should just remind ourselves, what is a tree? I mean, we see a bunch of them out the windows. Oh, okay, yeah, all right, we can go with the formal definition. So tree is a connected acyclic graph. This is one way to define. There's lots of ways to define trees. So essentially, in some sense, a tree is the smallest you can be in terms of number of edges and still be connected. And so that's why we say there's a cyclic, because if you had a cycle, you could pull out a single edge on that cycle and you could get smaller. You can also say trees are, so that comes to saying trees are connected and they have the smallest number of edges, which is number of vertices minus 1. It also turns out that another way you can think about a tree, we won't use this, but it says that between any pair of vertices, there's a unique path. And so this is a property of trees that frequently gets used in the literature. So between any pair of vertices, there exists a unique path connecting them. I don't want to say unique walk, because of course walks are allowed to jump back and forth along edges, but paths aren't. And so that's why we want to use the word path here.
And you did write walk.
Oh, yes.
Oh, no.
Yes, this is one of those things where you should not try to write and talk at the same time, but somehow people want commentary as you're writing. So it's a skill which I'm only about 60% proficient at. All right, so we know what a tree is. What does it mean to be a spanning tree?
that a tree that covers every vertex?
Yeah. So spanning here says all vertices are used. All right, good. So what do we have? Well, we'll do an example here. So the punchline here is, this is really an enumeration result. It says, if you want to know how many spanning trees there are, we have ways. We have ways. All right. Well, we'll pick a graph, hopefully not too big. So here's our graph. Okay, how many spanning trees does this graph have? Well, we can just start drawing them, and hopefully we don't miss any. So that's a spanning tree. Yep. And well, we could do the other side. That's a spanning tree as well, right? Or we could do zigzaggy.
Yeah.
And we could zigzag the other way.
And then you can like go around the outside and leave one out.
Okay, we could go around, doing around the world. And do. All right. So, is that it? Yeah, it is. It's not hard to convince yourself for a small graph that this is true. Okay. Well, all right. And so how do we count such a thing? Well, one thing we can do is we could just say, well, look, you could just look at all the ways that you could pick. Now, in this case, this is a 4-vertex graph. And so if I want a spanning tree on 4 vertices, I need 3 edges. So I can look at all the ways I could pick 3 edges. And, well, that might take a while. There's 5 edges. 5 choose 3 is a number. It's 10. And we can say, look at... Right, yeah. You could pick a triangle with an isolated vertex or a triangle with an isolated vertex. And those are the two that don't work. So we could say, okay, now we've looked at all 10 possible ways to take 3 edges. And we said, hey, we've accounted for everything. Now you might say, that sounds like a lot of work. But that's what's going to happen. So that's the underlying idea. Now, we don't need to know too much about trees. We do need to know a couple of nice facts. First off, a quick definition, and this, we can fit our nice fact down here. So what is a leaf on the tree? What's special about a leaf?
Degree 1.
Degree 1. So it's a vertex which has degree 1. So in other words, it's like one of these vertices that you see, like almost like you would say, like it's the end of a tree. And you think, well, what's the end of a tree? It's a leaf. Mathematicians had a lot of fun coming up with the names for these things. At least I hope mathematicians did it. I'd be sad if I found out I was computer scientists, like, oh man, it should be mathematicians. We should get the glory. All right. So, a question for all you graph lovers out there. What can we say about the number of leaves that a tree has? Does a tree have to have a leaf?
Yes.
All right. Somebody has said, aha. So a tree must have at least 2 leaves. Unless, of course, you're the really silly case, which is the single vertex, which will count that. But, it's like, okay, if we're not that, we have 2 leaves. This is our fact that we're going to need. Okay, good. All right, well, so how do we do this? Well, not surprisingly, we need to get into the Laplacian. So let's look at the Laplacian. And so for this particular graph, let's label and, all right, well, we can label that, say, 1, 2, 3, 4. So the Laplacian would be a 2, minus 1, minus 1, 0, and then a minus 1, 3, minus 1, minus 1, a minus 1, minus 1, 3, minus 1, and a 0, minus 1, minus 1, 2. Okay, so there's our Laplacian. And what are we going to show? Well, what we're going to argue is not so much this expression of 1 over n, lambda 2, lambda n, that product. What we're going to do is take a look at cofactors. Now, it turns out that if you take certain cofactors, you can show that this will be the right expression. All right. I saw that we wrote down lambda equals 2, not connected. We should also add, so no spanning trees. So that's what happens if lambda 2 equals 0. If we have time, we'll come back and talk about lambda 2. It actually has a name. And I know you're thinking, yes, lambda 2. But there's actually a real name attached to it. And okay, so what are we going to do? Well, the idea is look at cofactors. Now you might say, well which cofactor? Ultimately, it doesn't matter. But we'll just pick 2 cofactors on our diagonal, because then we don't have to worry about signs. When you go off, we don't want to have to worry about signs with cofactors. Okay, so what's a cofactor? I've used this word like 4 times in the last couple minutes without actually seeing if you knew what that meant.
A cofactor is so you delete. So what you're going to do is you're going to delete a row and column of your matrix,
Right?
and then the cofactor will be. So if you delete row I and column j, the
Right.
cofactor is -1 to the I plus j times the determinant of that submatrix.
Good. Good. So we're going to do, let's delete the first row, first column. And so we're taking the determinant of 3 minus 1 minus 1, minus 1 3 minus 1, minus 1 minus 1 2. All right. Well, let's find out. What does this turn out to be? All right. 3 times 3 times 2 equals 18. Minus 1 times minus 1 times minus 1 is minus 1. Minus 1 times minus 1 times minus 1 is minus 1. Then we'll have minus 1 times 3 times minus 1. That's a plus 3, but we have to subtract it. Minus 1 times 3, but again, that's a plus 3. We have to subtract it. And 2 times minus 1 times minus 1. That's a plus 2, but we have to subtract it. Okay, so there's 18, and we subtract a lot of stuff. And if we add up all this subtracted stuff, I think that's, you take off 10. Meaning, we have 8. 8? Well, that sounds like that number. Well, yes, that's the point. Now, you might say, okay, all right, Steve, I'm a skeptic. Do it again. All right, no problem. We have time. We'll do it again. Now, I would say this basically, you should only do this twice because there's really only 2 vertices up to symmetry. All right, so we'll cross out now the second row, second column. Okay, so in that case, we have the determinant of 2 minus 1, 0, of minus 1, 3 minus 1, and of 0 minus 1, 2. And you'll see these are definitely different matrices. And of course, different matrices, we should expect different values. 2 times 3 times 2, 12. Minus 1 times 0, 0. Now you might say, wait, did you need to add or subtract? Yes. 0 times minus 1 times minus 1, 0 again. 0 times 3 times 0, 0 again. But because I'm going diagonally up, I'll subtract it just to be consistent. Minus 1 times 2 is a plus 2, but we have to subtract it. And then 2 times minus 1 is plus 2, but again we have to subtract. So we end up with 12, subtract 4, which is 8. All right. So the moral is, we're going to actually argue that when we cross out a row and a column, and we're going to have it be the same row, same column, then what we'll get is the number of spanning trees when we take that determinant. That's the direction we're going. All right, so are we ready to pull out our big tool? So our big tool, which we've talked about before, I guess maybe I shouldn't say it's our mathematical tool, but from last time we called a certain matrix T. Do you remember what this was?
The signed incidence?
Yes. Right, good. So this is what we call the signed incidence matrix. And as you will recall, we have the vertices. The index is the rows, and the edges index the columns. And then in a particular column, you'll have one of the entries for the edge will be a +1, one of them will be a -1, and the rest of the entries are zeros. Which one is the +1?
Dealer's choice.
Dealer's choice. We don't care. There's not a right or wrong answer. Now you can try to sort of like, I'll come up with some obscure rule, and if I just get just the right rule, then life will be good. But that's not what we're going to do. Okay, so we already talked about last time that we said that the Laplacian is the same as TTT, right? The incidence, signed incidence matrix times the signed incidence matrix transposed. Now, if we come back up here and we talk about, well, how do we denote deleting a row or column? Well, we should come up with some good notation with that. So we'll temporarily abuse our notation, if that's all right. So I'm going to let L sub II, for the moment, this doesn't refer to an entry, but this will be the matrix L with the ith row and column deleted. Okay. Can we say something about LII in terms of T? And if we can, what is it?
The subgraph generated by the
Well, keep in mind that when you take the Laplacian matrix and you delete a row and column, what you have is not necessarily a Laplacian matrix. So you want to be careful about saying something generated by a subgraph. Now you might say, how do we know it's not a Laplacian matrix? Well, for instance, row sums are not zero. So that's a sign that it's not a Laplacian matrix, because the Laplacian matrix has that cool property like, yeah, all the row sums are zero. Woo, look at me. I'm zero. But you have some kind of the right idea. So don't think subgraphs, think submatrix. And just think about the size. So, for example, the dimensions of the Laplacian, what would it be? N by n, like number of vertices by number of vertices. After you've deleted, what's our dimensions? Yeah, n minus 1 by n minus 1. So I want to get something that should somehow shrink the dimensions down. But what could that something be? A mystery. Well, but our underlying graph doesn't necessarily have a leaf, right? So we have our leaf discussion will come up in a few moments. Yes. So if you think about it, what's happened here is when we delete the ith row and column, we're deleting the ith vertex, because that's the rows and columns are indexed by vertices. So what we'll do is we'll do T sub I transpose, where T sub I is T with the ith row deleted. So we only delete the row, because the row is the column. We're not deleting any edges. All right. So, good news, we've run out of space. So we can start on our new page. So far, so good? Now, so we're going to need the signed incidence matrix. The other tool that we're going to need is something called Cauchy-Binet. And we're not going to prove this. We're just going to use it. Now, what's the idea of the Cauchy-Binet formula? Well, Cauchy-Binet says, hey, suppose I wanted to take the determinant of a product of two matrices. Now, there's, of course, the famous formula. If I have two square matrices and I multiply them together, how do I find their determinants? Yeah, it's just the determinant of the first, determinant of the second. Okay, well, that's really cool. But what if my matrices I'm multiplying aren't square? What if they look like this? Now, you might say, when would we ever encounter such a thing? Well, so for example, if we had the signed incidence matrix with the ith row deleted times the other signed incidence matrix with the ith row deleted. All right, so we have to come up with some notation here. And all right. So I'm trying to decide. Okay, yeah. So we'll have, we'll call this matrix here our matrix P. This is our matrix R. And we'll say that B is equal to P times R. So then the punchline is that the determinant of our matrix B is found, and bear with me, this will, oh, I need to specify dimensions. Okay, how big should we make P?
By
M by P. M by P.
R
How about
S.
M by Q? Because we already have it's hard to distinguish a capital P from a lowercase p when you're writing on a page.
We did T. I thought this would be accepted.
Yes, I know we did T, but
That was so different.
but you could tell that the third T was in the exponent, so there was no confusion. So P is M by Q, R is Q by M. Okay, so here we go. So what the determinant is, and I have to make sure I get my formula right. We're going to take a look at where all subsets of Q. So if you're not familiar with this notation, when you see the square brackets, that means 1 up through Q. And we're going to look at subsets of Q. And we just have to make sure they're the right size. So the M element subsets. And now what we're going to do is we're going to take the determinant of our matrix P, where we have all of the rows but only the columns that correspond to S, and times that by our determinant of R, where we only use the rows associated with S, but we have all of the columns. And there we go. All right, so let's visually see what's going on. What we want to do is we say, well, we'd like to somehow have determinants of square matrices. And so if you notice here, the size of S is M. So we're going to have square submatrices of P. So what we're doing is we're really taking all the possible submatrices of P, which are going to be m by m. And the way you find these is you specify some number of rows. They don't have to be contiguous. So maybe we have 2 pieces. So we take, some number of columns in P. So we say, okay, take that submatrix there. And now you're going to take the exact same rows in R that you took columns in P. So that you have these pieces here are matching. And now you take the determinant there. And if you do this in all possible ways, lo and behold, you get the determinant of the product of these. Okay. This is not impossible to solve, but I don't have a proof memorized. If you really want to see a proof, you can find a proof in Proofs from the Book. So if you're familiar with the book, does everybody know about the book? So a few people are not nodding their heads yes, so we'll digress for a moment to catch our breath. Say, what is the book? So Erdős, mathematician, said, look, every theorem, every beautiful theorem is written down in the book. And for every beautiful theorem, there's one proof. The most elegant, the most insightful, the most beautiful proof. And that's the book proof. And then Erdős went on to say, you don't have to believe in God, but you do have to believe in the book. So the book is real. So anyways, there's a book called Proofs from the Book, which has lots of really beautiful, elegant proofs. And one of the chapters goes through and does Cauchy-Binet. And then later on, they do what we're doing right now. So this is a linear algebra result. I will convince you of one special case, because I'm pretty sure I can convince you of the following special case. Okay, what if our matrix, pair of matrices, were things that looked like this? Just one row, one column. How would you compute this? Well, if you multiplied these 2 matrices together, what would you end up with? You'd end up with a 1 by 1 matrix, right? 1 times 4, 2 times 5, 3 times 6. And how does one take the determinant of a 1 by 1 matrix? Yeah, it's what it is. So it's 1 times 4 plus 2 times 5 plus 3 times 6. All right. Now, let's see what the formula says you should have done. So the formula says, you say, all right, let's think of all the ways I can take one column. So one way I could take one column is to do the first column, and then I do the first row. And say, okay, now take those determinants. What would you have? You'd have 1 times 4. And then you say, oh, okay, well now that works so well. Let me go. Another way I could have picked is I could have just picked the second column and corresponding to the second row. And if you took the determinants of just the pinkish part, what would you have? 2 times 5. And I'm running out of colors. But, oh, here we go. I think this one's not too bad. I think it's distinct enough. Orange. Orange, you glad? I used colors. Ah! Okay, sorry. But again, it's 3 times 6. And now you add them up in all possible ways. So it is consistent. And so at least in one case, it's true in one case. And so by engineering standards, it's always true. Okay. But if you want to see a full proof, again, you can look it up in Proofs from the Book. Okay, so we're ready. Here we go. We're trying to compute the determinant of LII. All right. And this, by the way, is where we're getting our 1 over n, lambda 2 times lambda n. That's just a property of our matrix. Now, how do we do it? Well, we're going to have a sum. Now, let's think about what's going on here. So when we talked about sums, we were talking about summing our columns. Now, in this case, P and R are going to be the same matrix. Okay. Let's just write, I'll add one more step. That's the determinant of Ti, Ti, T. Okay. So now both P and R are the same matrix. They're this T sub I. So let's think about what this subset corresponds to. So when we were talking about subsets before, we were talking about corresponding to a selection of rows in the first matrix. Sorry, selection of columns. Selection of columns in the first matrix. But what do the columns correspond to? They correspond to edges. So this is going to be a sum over all S, a subset of the edges of our graph G. And how many edges do we need?
N minus 1?
N minus 1 edges, because that's how many rows we have. Now, if you think about this, this says, oh, we are summing over all ways to select N minus 1 edges in our graph. Okay, so this is promising. This is really promising. So it's like, oh, okay, we see what you're doing here. So now, if we write down what we have, well, we have the determinant of, and again, I'll just copy what we have, Ti, we have, in this case, all the vertices. So M is just all the rows, so it's the vertices of G, and then it's the edges of S. And then if you say, well, what's going on over here? It's the same thing, it's just the transpose of it. Determinant of the vertices of G, the edges of S, and transpose. Well, the transpose doesn't change the determinant, so I have the same thing twice. So this is the sum over all S, subset of the edges of G, where there's N minus 1 edges, and then we're going to take the determinant of the signed incidence matrix, where we take, well, actually it's not V of G. I have to be careful here. What is it? It's not V of G, right, though I wrote it down. It is V of G minus I. Yes, because we deleted the ith vertex. So the determinants Ti, V of G minus I, oh, I'm okay here, minus I, comma, S, and, okay, I feel like I need another squared. Since these are the exact same. All right, so what's the rest of the proof going to look like? Can we kind of see where we're going? We're squaring something. So what would we like to be true? So every time we add over these n minus 1 edges, what would we like for this to do?
Indicated for being a tree, so 0 or 1, 1 can only be a tree.
Yeah, we want it to be 0 if the edges of S are not a spanning tree. And we want this to be 1, and when I say 1, the whole thing, squared, 1, if the edges of S are a spanning tree. So the last thing for us to do to finish is to actually verify both of these statements are true. All right. Good. We're doing great. Any questions? Assuming I haven't missed any other silly things. Okay, let's then take a look at this determinant. We're not going to fit into this space, just so you know. That's all right. We always have plenty of paper. All right, so our goal is we're going to consider, we have our signed incidence matrix, and we have all our rows. So this is V of G minus I, but we've specified our edges. So we've specified a set of columns S, size of S is n minus 1. Okay, so case 1. Let's start with that we don't have a spanning tree. All right. Well, so we know S is not a spanning tree. What does that tell us? So if we're not a spanning tree, what's true? Okay, so you have a cycle. That's true, 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 true. True that, true that.
Wait, if you have a cycle, how do you not have a spanning tree?
Yeah,
But a cycle contains, but you just remove an edge.
Spanning tree is a subset.
It means it's not connected.
Yeah. Right. So there's a lot of ways to say something's not a spanning tree. Now, of course, the question is, what's the way that's going to help us?
That appears to be the question between our interpretations, yes.
Okay, all right. We'll say S is not.
Yeah.
How's that?
Okay. Is not.
But it doesn't change the answer. Because you have n minus 1 edges. So if S is not a spanning tree, if S, anyway, all right. S does not have a spanning tree. Yeah, that sounds like a mathematician wrote that sentence. All right, S is not a spanning tree. So there's lots of things that we could focus on. I'm going to focus on not connected. Okay, so our set of edges form 2 or more components. Now, the thing we have to be careful of, and this is a foreshadow of our challenge to come in just a moment, is we kind of have this weird vertex out. And that weird vertex out throws a wrench into things. Now, the good news is that's only one vertex. We have 2 components. So what must be true about one of the components? But what do you mean by it must have been left the same? Yeah, I can only belong to one of the components. So there's some component which does not contain I. All right. So now let's think about what's happening. So I'm going to take my T sub I, B, G minus I, S, and so we have a component. So let's just say without loss of generality, we can assume that these are the vertices in the component not containing I. Now, question. What happens if you sum these rows? Well, think about where an edge could be. An edge might not be in that component, and if the edge is not in the component, what are going to be the entries here? It's going to be all zeros. Or, right, we could have a different edge, and in that case, we'd have both a +1 and a -1. Now, why do we know we have both?
Because otherwise they're connected.
Okay, right, because they're in the same component. And the thing is, we've deleted row I. So we've deleted vertex I, but vertex I is up here. Okay, so what's the sum of the rows?
0.
It's all zeros. All right, so if I have a subset of the rows, a non-empty subset of the rows, and I sum them and I get 0, what's true about this matrix? Well, channel your matrix right now, your linear algebra self. I am a linear algebra student. I see that I have rows. When I add the rows, I get the 0.
Is that it's linearly dependent.
So the rows are linearly dependent. So what do I know about a matrix which has linearly dependent rows? The determinant is 0. So the rows are linearly dependent. So the determinant is 0. Which means that when we pick a subset of the rows, a subset of the edges, and it's not a spanning tree, then we're not going to get a contribution. It's going to be 0, if you like. 0 is what's being added.
Sorry, we're saying the determinant, isn't this matrix not necessarily squared?
Well, it is square, because if you look at how many vertices we have n vertices, but we subtracted 1, so that's n minus 1. And how many edges we have is n minus 1. So it is a square matrix.
Yeah.
Yes. Okay, so we're halfway done. All right. So let's do the other half. All right, case 2. S is a spanning tree. There we go. Now I'll get it right this time so that we don't have any controversies. Okay. Well, now we have to think about what's happening. And it might help to think about, Steve said something at the beginning. It's going to be really helpful at some point. About the leaves, yes. So we have a spanning tree. Let's assume that we are not a one vertex graph. Sorry, what? Right. So our tree has at least 2 leaves. Now notice, before we had at least 2 something, and then we said, aha, well, we can make a conclusion. So we want to make a similar conclusion. What's our conclusion we want to make here? One of the leaves is not I. Great. So the tree has at least 2 leaves. So some leaf is not I. Let's give that leaf a name. What would you like to call it?
J.
Okay.
Oh, yeah.
Okay. How about we call it L sub 1? Because we're going to talk about things. So now I'm going to permute the matrix. Now permuting the matrix only changes the sign of the determinant. And because we're squaring things, changing the sign doesn't matter. All right, so now that I waved my hands and I convinced you, I'm going to say, okay, L1 is the leaf, and it's next to an edge. Let's call that edge something. Let's call it E1. So some leaf is not I. Call it L1. So this is the vertex, and E1 is the edge, because that will not look confusing in all my L's and my E's. So, a question for you. What are the entries in this corner? And why is that?
edge.
Yeah, because the leaf is incident to the edge.
Yeah,
What are the entries here?
all zeros.
And why is that?
It's a leaf.
But why does that make it all zeros?
It's no other edges.
Right, because it's only incident to one edge. Okay, so now think of it as we've now plucked off that vertex L1. We now have another tree, because if you take a tree and remove a leaf, you have a tree. So what's true about that tree?
It's got a leaf that's not I.
It's got a leaf that's not I.
Oh, no.
Let's call that leaf L2.
Ooh.
And that has some edge E2. And now, what can we say about the entries here? It's plus or minus 1, and along here, zeros. Well, and now, repeat. And what's going to happen?
I
So,
don't necessarily know its relationship to L1.
what do you mean? Yeah, well, L1 and L2, we don't know. They could be very far apart. They could be like L1. Now L2 is right there. So we don't know. Like so we don't know what this is, for example. We have no idea here. But the moral is, if we keep doing this, so what we've done is we've done a relabeling. What we'll end up with is in the subdiagonal, below the diagonal, it's all 0. And then on the diagonal, it's all plus minus 1. And above the diagonal, we don't know. But we don't have to know. In fact, we don't even have to care. Because what's our goal? We want to know the determinant of this. So what's the determinant of this matrix? Yeah. So the determinant is plus or minus 1. Now, we have to be careful because we've also permuted. So there might also be the negative of plus minus 1, meaning that we might have minus plus 1. But after we square, what happens? So yeah, so squaring, our contribution is plus minus 1 squared, which is 1. So for every set of edges, which is not a tree, we get a contribution of 0. For every set of edges which is a tree, we get a contribution of 1, which, if we pull back, says that, lo and behold, this is the number of spanning trees. And that's the result. All right, let's in 1 minute prove Cayley's theorem. I think it's Cayley's theorem.
The labeled spanning trees as n to the n.
Okay, somebody knows Cayley's theorem.
I looked at it today.
Cool. Did you see a proof of it today?
No, it was not on the note card.
Well, you're about to see a proof. So Cayley's theorem. So Cayley's theorem is about the number of labeled trees on n vertices. And it is true that the result is n to the power n minus 2. Now, how can we prove this? Well, what do we mean by labeled tree versus unlabeled tree?
It's all trees with vertex set square brackets in.
Yeah, so for instance, if I was thinking of an unlabeled tree, I wouldn't put a labeling here. There'd be essentially one unlabeled tree on 3 vertices. If I have a labeled tree on 3 vertices, how many different labelings do I have? He asks as he draws 3 trees.
Yeah. 1, 2, 3. 2, 1, 3.
Yeah, 1, 2, 3, 1, 3, 2, and a 2, 1, 3. These are labeled. Now, here's the thing. We can count the number of labeled trees by saying, hey, this is the same as the number of spanning trees. Anyone guess which graph we're going to go with? Sorry, what?
Complete graph.
Yeah, the complete graph of n vertices. So we just have Because when we talked about spanning trees, we had labels underlying it. Okay, well, what are the eigenvalues of Kn for the Laplacian? This is something we talked about. I'll tell you the first one is 0, if that helps. The second one is n,
Just have n center.
and the rest of them are all n. So there's n minus one of them. Okay, so now, by Matrix Tree Theorem, we get that the number of spanning trees is 1 over n times n times n times n. Well, how many n's do we have? There's n minus 1 of them. So 1 over n times n to the power n minus 1, which is n to the power n minus 2. And we're done. And there's other proofs of this result, by the way. There's proofer codes, but this is a nice application of spectral graph theory.